Hello everyone. So let us start our journey on the sectorial kind of from a generation side. So not sectorial analysis from a consumption side, but from a generation side, let us go sector by sector. As I said in the last class that let me start with solar photovoltaic or solar as a first sector which we will get into. So let us start with some basics of solar and let us start from something that what is happening in the solar domain, why solar is popular, why solar is becoming such a integral part of this energy transition story, what is so good about it, and but given that what are the challenges, what are the expected fear from this whole growth story, fear in terms of stability, fear in terms of reliability of this sector, fear in terms of material resources, fear in terms of finances, or whatever are policy level challenges. Let us start looking deeper into this. But as we all know that solar energy is emerging as one of the most important technologies for achieving global net zero energy transition. It's very obvious. You have seen all this data in last few lectures. And just to talk in terms of simple terms, it's a simple technology in which basically panels are installed in abundance, and that panels, when the light falls on to these panels, these lights is absorbed by these panels and converted into electricity. And once it is converted to electricity, you can tap that electricity, you can tap that generation of electrons and make them go to the places where you want them to go, and you can utilize them the way you want to utilize them. And so it's not a new technology per se. So solar, many of you might already know, like this was developed maybe in 1960s and maybe invented much before that. But in terms of real development of silicon solar cell, first initial solar cells which were made around 1960s where it started. It then was put in shelf because it was found to be too expensive, too inefficient, and it was always put as a technology which was always for niche uses, that not as a mass use. One spurt in this came around when the oil crisis in 70s happened. So around that oil crisis, some kind of a resurgence in this technology happened. But again, as soon as we kind of solved that issue, this again went into a non-focus zone. But the whole focus on this solar energy kind of started when we started looking into this climate crisis as a major area of concern, and when we started looking into climate changes as the major area of concern, that's where we then started looking into that what are the potential technologies which can lead to the amount of energy generation that we need, and without emitting much. And that's where solar was taken as one of the major areas of focus, and that from there it has kind of grown very rapidly over the last few years. And what has led to that fast growth is declining cost, supporting public policies, and expansion of global manufacturing capacity. Manufacturing capacity has been a real success story in this sector, because this is the manufacturing sector growth which has led to this declining cost. And we look into this more, and that what has led to what, and in this specific sector. Just touching upon some of the fundamentals. So basically, as many of you already know, that solar energy basically originates from nuclear fusion reactions occurring in the sun. The earth receives a good amount of solar radiation. Many of you will remember some of the numbers that I talked to in terms of energy earlier. The solar radiation is so abundant on which is falling on the earth, is that if there was possibility and if you can somehow do that, the total solar radiation which reaches earth in 2 minutes, I'm talking about the overall earth, if you take earth as a sphere, as an approximate sphere, the total amount of radiation which was falling on the earth in 2 minutes, if there was some way to capture it, if there was some way to you can capture it all and store it and use it for future use, you can basically have enough energy on the equal to a net annual consumption of the overall earth, and if you can convert that rightly. So if you could do that, that's the amount of potential that we are talking about with respect to solar radiation. That's the amount of energy source that we are talking about. And the best part for this is it's renewable. It comes every day and it doesn't deplete any of our resources. So that's the most beautiful part of this. In terms of geographical areas, so global south receives the higher sun, the potential of the global south is much higher in terms of sun potential. So it becomes a very interesting thing, because if you look at from a geopolitics perspective, or from the growth versus need for transition, or versus the responsibility of transition. When we talk about transition responsibility, remember we talked about this earlier, that primarily some countries have developed much faster, but the pressure of transition is coming on all the countries, and some of the countries are struggling with maintaining its development path to its transition path. And for them, since solar radiation is interestingly falling more onto those countries itself, which is called global south, which is starting the transition journey. So for these specific countries, including India, this becomes a very strategic source, not only as a source for one of the sources for energy, but becomes the strategic source for energy, because one, it is in abundant, and second, it is available more in specific geography, and given the cost figure of this specific technology, this becomes a very interesting transition source for this specific part of the geography. Talking a bit more on the physics side of it, and there's a reason why I'm also showing you this graph, is that if you just look at the solar radiation, the yellow curve kind of shows you the solar radiation which is on top of the atmosphere, but once it kind of filters through the atmosphere, remember I talked to you about the multiple layers of the atmosphere which is present over the Earth's surface. A lot of absorption, lot of scattering, lot of back reflection happens, absorption which happens in those layers depending upon the specific molecules, depending upon their absorption peak around this sun radiation which is falling. If you start looking into this, the actual radiation which is falling on the Earth is given by this red curve. And so typically here how much the sun radiation is falling is about 1.35 kilowatt per meter square, but what typically reaches the Earth is about 1 kilowatt per meter square, and that's why in most of our calculation we kind of use 1 kilowatt per meter square in most of our calculations when we are doing the solar radiation power generation. But if you want to go in physics of it, you can go further deeper into understanding that there are direct radiation, there are diffuse radiations, and then how much direct radiation kind of contributes, how much diffuse radiation contributes, and what are their nuances. So that is really going into solar technology part of it. So let me not get into that in this specific course. That is a different course altogether to talk about. Then how does it gets converted to energy is that it could be converted to energy in multiple ways, but two most popular ways are, they could be a solar thermal radiation. So remember, while there are multiple zones in which this radiation could be divided. One zone is the UV zone, which is kind of a zone which can lead to some unwanted effects like skin irritations or skin redness or issues like this, and this is the primary zone which is useful in some very minimal thing for killing bacteria specifically, but not very useful when it comes to energy generation. From energy generation side, two major zones which are used is that we have the visible range or we have the infrared range. And look at the long tail of this infrared range, and this infrared range is nothing but can lead to a lot of heating phenomena. And so given that such a big tail of heating, so initial solar development, a lot of solar development initially was all done around that, using this phenomena that can be used sun as a heat source, and that heat source then can be used to generate energy or to directly use that heat in a manner in which this heat can directly be used as a source itself. So initial path was all about radiation to heat and then directly using this heat. And then later on we also start talking about if you can convert this heat to electricity also. So that is one path, and in that what was typically done is that you kind of have a reflector in which this is concentrated solar power, you can use it using a parabolic trough. So what is usually done is that the solar radiation kind of falls onto these parabolic shields, and then it gets reflected to a tube which is running on top of this. So it's kind of a parabola in which there is a tube here. So sun radiation falls onto it, and it's so designed that all gets reflected to back to this tube, and this tube kind of contains a liquid which is heated, and then that heated liquid is then put into a kind of a generator, and in that from that generator the steam of that heat is used to convert that electricity, and that electricity can be then put on the transmission system. So this is one of the very popular means of doing it, and given the long tail of heat also, so this not only taps into the reflected visible range, but it also taps a lot into reflected heat also, and then overall huge amount of solar energy, like starting or virtually the whole solar radiation graph can actually be used for thermal uses and converting thermal to electricity. That's a very powerful thing for this thing, but still it has a limited uses. I'll tell you why. The more popular means or using sun as an electricity source these days is called photovoltaic conversion, in which the radiation falls onto a material which can absorb this solar radiation, and in this it is converted to electricity via semiconductor p-n junction route, and that is becoming very popular given the simplicity of this thing. So remember, so now if you look at this structure very carefully, this is a very complicated structure to make. So it is sitting on a big mechanical structure in which this parabola has to kind of move around the sun direction, and given the size of the whole thing, the whole infrastructure becomes such a complicated structure to make, and so mass deployment of such structures becomes very difficult. And so this specific module, which is a very simple rugged kind of a slab which is just put it out there and just kind of converts it into electricity, is becoming very popular mean of electricity conversion. But there is certain dependence on material type here, and this I'll go into further in next few slides. But once the solar light falls onto it, there is a charge you can kind kind of convert this charge to specifically to charge a battery. Then you can use it either inverter to convert it to AC load or directly use DC load from the battery itself. So this is a very popular way of converting a solar energy to a electrical energy. Further, this technology can be both passive as well as active. So in terms of active uses, what I talked about is that using the photovoltaic panel, converted it to electricity. Those photovoltaic panel can also be put on the walls also, where you can have the side sun radiation which is kind of coming and using the more area, surface area basically. So putting on the wall basically means using more surface area. You could also have sources where you can also directly use this as a heating source for water directly for a pool or for other uses, for home uses also. You can convert this directly to heating purpose also, for bathing purpose also. It can be used a lot. There could be another way of using the sun radiation, which will be a passive kind of a phenomena, in which what we can utilize, that we can utilize the sun angular path also. Like for example, sun goes to almost 80 degrees in terms of its latitude in summer days, and in winter it goes only up to 60 degrees. So given that angular difference from the vertical, so this goes to almost 80 degrees in summers, and it only goes up to 60 degrees in winters. So if we can make our windows in a way that windows only allow the winter sun to come in and summer sun to kind of stay out, we can use this as an indirect source of heating also, because that sun energy will bring in the heat along with it, and we can use that as a passive means of heating our houses also. We can also utilize this otherwise also, that both during summers and winters we can use it as a direct source of light also, that we can have daylighting phenomena, inside daylighting phenomena, not using artificial lighting. So there are a lot of passive energies which are also kind of is also being developed for this sun path also. But for this specific lecture, we will be focusing more on the active technologies, and under the active technologies, we will look into what is happening around it. Right? So as we talk, two most popular active technologies that we have been talking about was solar thermal technology as well as solar photovoltaic. So solar thermal kind of works in a very simple means. One of the things that I have shown you, that sun radiation falls onto a parabolic trough, and that parabolic trough kind of reflects the sun energy to a tube which contains a liquid which is then heated up, and that heated liquid kind of produces a steam which is then converted into through a steam engine to convert to electricity. That is a very classical way of converting it. Other way of doing using this sun energy is directly through flat plates, in which the direct radiation or diffuse irradiance kind of falls onto a plate. We have liquid which is on the backside of it. So here the sun energy is trapped into a kind of a glass slab. So what happens is that the sun radiation kind of goes in, and then it is reflected. Some part of it is absorbed by this tube, some part of it is reflected, and then it is reflected back using this glass. So through this multiple reflection, you can kind of absorb this sun energy a lot. So while this is working on the kind of a parabolic reflection phenomena, this is working on multiple reflection phenomena. So both have its advantage and disadvantage. The advantage of this is that here the heat can be very high, and it can be taken to almost 3000 degree Kelvin, or very hot temperatures are possible, which can also have its use in industries like steel industry or any other industry which requires very high temperatures to be used for its processes. So there also these kind of phenomena can be used. On the other hand, these kind of flat collectors have an advantage that they are very simple to use. So they are used a lot in this solar water heaters at home. This is a very popular technology which is happening on that end. So this flat collectors have become very popular for home water or industrial water heated uses, because you can directly put that as a plate, simple plate structure, which can then simply convert the solar heat energy and trap that solar heat energy and convert the water to a hot water. So that is used a lot for domestic water heating purposes, process electricity purpose, and using this route it can be used using the electricity generation route also, but it has its own limitations, as we can see that the structure is very complicated, and the structure is very expensive to kind of maintain the whole thing, and that's why this thing has become very popular, but this thing has not become so popular as of now. So if you look at it and consider the solar power, that's why the growth has been very muted. Almost no growth has primarily happened because of the complex assemblies and cost remaining very high because of this whole optics which is needed as a prime structure for this. So there have been some very interesting developments which has been done in some parts of the world where big reflector based systems were being put in, where those reflectors were kind of getting tilted and they were focusing the energy back onto a high tower, and the temperatures which was kind of achieved in these specific towers were very, very high. So this is specific installation which has happened in Middle East somewhere. And but there could be another industrial kind of uses where at industrial level there could be mass deployment where water heating or for also for some liquid heating, as I said, for some specific industrial uses also this has been used, but very, very muted growth. As you can see that the growth has not been, almost very minimal, because of the very complex kind of structure which these things kind of bring in. Solar water heater on the other hand has been more popular as a source, and the reason for that is the simple structure of it. It has seen a growth which has been pretty impressive and very high efficient with respect to when it comes to just the heating phenomena. For direct heating requirement, this could be almost 3 times higher than the photovoltaic technology per se. China has been the biggest implementer. Turkey or some Brazil and India has been kind of distant second in this whole kind of transition journey. But what we have seen is that this growth is kind of plateauing out because a lot of installations have already taken place, and it's only a replacement market which this thing is working around. So this is data from 2024 which say that on a year growth basis, China actually degrew that year, India degrew that year, Brazil and Turkey kind of grew that year. But it kind of changes every year. If you look at 2023 or if you look at 2025 data, these numbers can be slightly up and down. But overall what we are seeing is that this technology, though very efficient for purely domestic and industrial water heating purposes, is kind of plateauing out at because of its limited uses for specifically for, as this is only a water heating process technology, which is primarily it is being used for. On the other hand, the solar photovoltaic system which we have been talking about is a kind of a panel kind of a structure which converts sunlight directly into electricity. And what happens is that sunlight falls onto a structure which is a semi-retired structure, which is a PN junction structure. And when that PN junction structure is there, when the sunlight falls onto it, thus the sunlight generates a pair of electron and hole, and then we can then collect this pair of electron and hole and separately on the 2 electrodes on both sides of the protostructure. And by collecting this, the electron and hole pair separately, and if we can keep them separated and let them not recombine before they are collected, we can have electricity we can be generated using this, and we can then connect it to an external load, and then through that electricity can be tapped into this thing. Very, very simple structure, and without moving mechanical parts, making them highly reliable and scalable. And that has been the real strength of photovoltaic technology per se, because of its ruggedness of and ease of use has been a prime thing in this. So this structure is a kind of a modular structure where each of these panels comes, like when I started working in the industry, they were coming out 200 watt per panel. These days panels are about 550 watt per panel. So, but as you can imagine that since it's a kind of a modular structure, so you can really scale it up the way you want to scale it up. So you want to put at home for 2 kilowatt system, you can simply put four of such panels, and you can want to put gigawatts of these plants, multiple big plants worldwide. You can put thousands and thousands of these panels in series and parallel the way the structure is. So very, very modular kind of a structure, and given the modularity of this structure, this becomes a very powerful technology from that perspective, that very rugged, very simple to use, and it's really modular uses which come. There are multiple kind of technologies which are being developed around this thing, which is if you look at generations of solar cells, so kind of generation of solar cell started with silicon and gallium arsenide as the first generation solar cell, then it moves to more thin film solar cells, and from those thin film solar cells then we are moving to more organic solar cell based structure. So this has really worked around that wafer based solar cell kind of structure came first, where we were talking monocrystalline silicon, polycrystalline silicon, and gallium arsenide as the initial technologies. Then the thin film solar cell, because it uses the main material here specifically with respect to silicon is about 150 to 200 micron, that's thickness of each layer. And since the material uses was very high, so it was thought that maybe we can do away with such high uses of material by going to thin film solar cells. So we started using amorphous silicon, calcium telluride, CDT or CIGS, or multiple kind of structures which are developed. And remember, this is the era when all this development were happening, or the era when silicon used to be the key bottleneck for this industry's growth, because silicon costs were very high. Silicon was primarily used for electronic industry in the solar industry, and no specific silicon was developed for solar industry before that. This whole transition started around 2000, early 2000. I'll touch upon this point as we kind of go along, what led to this phenomenal growth of solar energy. But around this thing, a lot of these technologies were being thought through. Currently also a lot of work is being done on the perovskite solar cells, organic solar cells, and quantum dot solar cells, and all these things are being talked about because still there are some bottlenecks with respect to silicon solar cell technology is because it requires very high temperature for it to process, and given that high temperature which is needed for these solar cells to process, people are talking about low temperature processes and using materials which are available in abundance, and given that a lot of different materials are being tried. But and how does it usually works is that light falls onto PN junction and then it kind of generates both current and voltages. It can be characterized using something called as a fill factor, or and then we try to maximize that what is the area under this curve, that how reliably this whole thing is generating, and then so I'm not going to physics of it, but what needs to you need to worry about is that there is a thing called efficiency of these solar cells, and these efficiency depends upon that what is the maximum power that these panels can generate or these solar cells can generate. This is depends upon the maximum voltage and maximum current which these materials can generate, and depending upon the incident optical power. So now how much voltage can they generate, how much current they can generate, depending upon it depends upon the material that they are made up of. So it's basically a material science field, which kind of materials type of materials that is used as semiconductor materials, that determines that how much is the maximum power that you can generate with this thing. Typical efficiencies, I'll come to this in next couple of slides, is what it determines that the area of the solar panel which is needed, and I want you to keep very good eye on understanding these two phenomena, that what is the difference between the CUF and efficiency. They are not same. So lot of students confuse in this thing that capacity utilization factor and efficiency, they start mixing it up, but they are two different phenomena. So efficiency is simply a term that how much of optical power is falling onto these panels, and how much of that optical power which is falling onto these panels is getting converted to electricity. That is what is determined by efficiency. For how long, for how much duration this power can be generated is determined using something called as CUF. So I'll talk more and more about this during the solar lecture, but you please keep in mind about this thing whenever you are solving any questions, whenever you are designing any system, please keep in mind these two things are separate. Efficiency only determines. So what does efficiency lead to? Efficiency basically leads to, since it determines that how much of optical power gets converted to Pmax, it determines that if you are trying to generate X amount of power at any given time, so it determines the area which is needed for this solar panel deployment. So suppose you need 10 kilowatt hour or 15 kilowatt hour, from that you can then determine that how many kilowatt of solar panel would be needed given this efficiency, and depending upon that then determine that what is the area of the deployment which is needed for the specific power to be generated. But for how long that power will get generated during the period of the day, that will be determined by CUF, which is primarily determined by the solar movement, that how the sun is moving, for how long the sun is out there, for how long sun intensity is high enough for it to produce meaningful electrons when the sunlight falls onto these panels. So these are two very different parameters which you should keep an eye on it. So this is what CUF is. So efficiency, as I said, that is simple incident optical power Pmax divided by that. Capacity utilization factor is that how much is this talks about the intermittency of the solar power, because solar radiation varies with time. Irradiance is not same throughout the day, and basically then CUF, what it measures is the actual electricity generation to the maximum possible generation. So maximum possible generation is that if sun was shining with the same intensity for 24 hours, 365 days a year, then you will be generating some certain amount of energy, but that is not the physical fact. So what it actually tells you is that what is the actual generation versus the divided by rated capacity and the number of hours that a sun is falling. So this number of hours per year is what kind of limits this actual generation is kind of getting limited by, because sun is available only for a fixed number of hours per day, and then it means the sun is typically available per only about a certain number of hours per day, so a certain number of hours per year. that is what sun is available for, and that kind of limits the capacity utilization. So since the capacity can only be utilized during the certain portion of the day, that's why there is a phenomenon called capacity utilization factor, and that capacity utilization factor typically for India is between 18 to 20%. It varies from geography to geography, that how close you are to direct sun falling is with respect to some other environmental parameters also, that how much is irradiance is falling onto that specific land area. So typically CUF for India is between 18 to 22%, and more high irradiance is seen in areas like Rajasthan and Ladakh. Reason for that is very simple, because the ground below the solar panels is also reflective. So while the solar panels are installed, some amount of absorption takes place directly. There will be light reflected from the ground, which will also go up again, and it can be reabsorbed in the system. And since this can happen, so that's why the CUF of that specific, that's why net irradiance which will be falling onto these panels in these specific geographies where ground is very reflective can have higher CUF, and that's why CUF in Middle East is higher than CUF in India. You can simply calculate from that. And if CUF is higher, it would mean a lower LCOE. Like, so you can start linking the LCOE formula to this, and you can start putting this whole picture together. So, but this is what CUF is, and so what CUF kind of include is day-night cycles, include seasonal variation, includes dust and atmospheric conditions also. Now, this is important for you to understand that this CUF is also not a constant parameter, that once you do the installation, this CUF will not remain as a constant thing, because what it does talk about actual generation. Now, what would this actual generation would mean is that you are assuming certain amount of irradiance falling onto the actual PN junction, and if there is a dust accumulation which is on top of this panel, and so this can lead to lower irradiance reaching the panels, and which will lead to lower generation, and so your CUF will go down. And that's why for a country like India, the another challenge which comes is that when you start deploying these technologies, the challenge which comes for a country like India is that given that we are in general having a dusty atmosphere, so for us to keep these panels clean becomes the key worrying factor. So why the solar capacity factor is low? Because of the intermittency I will talk about is sun angles and seasonality. I will talk about environmental factors like cloud, dust. There could be temperature effects also which could be there, because usually these solar panels operates at very high temperature, so it can lose efficiency, though this is more thing which will lead to lower efficiency than the CUF, but since it will also lead to lower generation, so that's why it can get impact. This is a factor which will impact both CUF as well as the efficiency of the panels also. There could be geographical location issues also. There could be soiling and dust issues also. So I will talk about this in bits and pieces, so not repeat here. But given the simplicity of this technology, like it's a very simple technology where you can simply put a panel, you can let it sit there, and it can simply keep on growing energy. The growth in this sector has become very, very impressive. And if you look at on a year-on-year basis, the total deployment in this sector in 2023 was about almost 1600 gigawatts. Now compare it to 6 gigawatt of CSP. So we are not even talking apples to oranges anymore. We are talking some very, very two different words apart, because given the simplicity of this whole technology, and given the economies of scale this has been able to achieve, because given the simplicity of this whole thing. So solar is the highest growth amongst all option. Like in last 10 years, the deployment has been more than 100 gigawatt plus in just last 10 years. And one country which has been specifically responsible for this is China. The highest amount of deployment which has taken place is in China. India is, as of today, as we speak, India is the third highest deployer. And in terms of generations also, India is becoming the third highest generated as of now, after United States and China. But India is expected to overtake United States after a certain period of time. But as of now, India stands at third. But the growth has been really phenomenal. And while we are talking that efficiency, in terms of efficiency also, since I talked about two limiting factors here, one was efficiency, another was CUF. And why will efficiency is important is with respect to land requirement around it. So a lot of research continues to happen in this line. I will not go into physics of those research, but as I already mentioned about it, that it highly material dependent. And so a lot of research is happening around it, and typically what we use is we use monocrystalline silicon solar cell or multicrystalline solar cell. So monocrystalline solar cell is typically hovering around 26-27% efficiency, or multicrystalline around 24 at a research level. From the research to mass production, we are talking about monocrystalline giving efficiency about 24%, and from monocrystalline from 24% giving a mass level of 20%. So that's kind of efficiencies that we are typically talk about. So typically installations that we are doing typically on ground these days is about 21 to 22% in terms of the cell level efficiency, and module level efficiency will be slightly lower than that. So this is the kind of typical efficiency. For a typical calculation, what you can do is that you can take, for a rough calculation, you can take typically 20%, but there are more reliable softwares through which you can design the whole thing. But typical efficiencies varies from 15-20%, while advanced solar cells like gallium arsenide can go to more than 40% efficiency, but they're very expensive material, very expensive process to make these panels. So they are primarily used for extraterrestrial kind of uses like spaceships or satellites which are going in the sky. They use these technologies. What is coming up more on these lines is that new technologies is coming up. We are talking about technologies like perovskite, which is coming up, which is showing good efficiency of about in high 20% right now. There have been thin film solar cell which has been hovering around, organic solar cell which has also been hovering around. So the multiple technologies are being talked about. Solar cell efficiency is looked into by all these things by material change. But if you look at the mass deployment, if you look at how this whole growth of solar sector has taken place, if you then track it, Fraunhofer, this analysis is done by Fraunhofer using ITRPV data. If you look at it, while there was some distribution of solar cells around 2014, where you could see a P-type multicrystalline, P-type advanced technologies, mono was there, another thing, some more mono was there, N-type solar cells were there, some CDT was there, some CIGS were there, some alpha silicon was there. There was a distribution of solar cell technology which was there around 2014, and which you can see from here also that there was multiple technologies which we were talking about. But as we have grown in manufacturing, as we have stabilized in manufacturing, as manufacturing sector has started to kind of get more and more stable and economies of scale are kind of setting in, what we are seeing is that monocrystalline solar cell, given that their efficiency is higher, and given the land, as soon as the efficiency is higher, the land requirement will be lower. So given that fact, and economies of scale has been achieved in this, cost is pretty impressive, and they are very reliable. Like we are talking about perovskite, we are talking about organic solar cells, we are talking about all those technologies. The issue with all of them has been the mass manufacturability of it or the reliability of this whole process. So organic solar cells, though they have been there around 15-20 years now, they have not been able to give very good reliable life at a mass deployment level. So while they have remained there, they have not been able to have a good break-in in the whole ecosystem because of given the reliability of the whole process. Similarly is the story of the perovskite as of now. So though a lot of research is happening on that end, let us see how does it grow, but this is the fact as of today. On the other hand, monocrystalline silicon solar cell have shown very good reliability. The life of these panels could be somewhere between 25 to 27 years. And given this big life, it becomes a very reliable, rugged system to kind of install once and kind of have a reliable power source from there for next 25 to 27 years. So if you look at in 2024 as a deployment, so in all thing, what you can see is the multicrystalline silicon technology has disappeared because monocrystalline people have been able to master. And again, I'm not going into what multicrystalline is, what monocrystalline is. Please, whoever has interest on these lines can read more, or if they want to contact, they can contact me to understand it better. But monocrystalline solar cell has overtaken the market. There is some bit of thin film solar cell which is remaining, which is about 2 to 3% of the net market share, and that too also only one company, which is First Solar, which is holding on to their technology onto CDTE, cadmium telluride, as one of the technologies for this thing. So, but in terms of the net deployment worldwide, you can see that it is primarily crystalline silicon technology, and in that also primarily monocrystalline silicon technology, which is primarily dominating the whole world. And if you then look into it has continued to dominate the whole world from many years now, and slowly it has kind of overtaken the whole world from that perspective. And given that we have been able to achieve such a big deployment worldwide, what has that led to is that it has led to very impressive cost which has kind of come up. But before I go into cost curve, actually I have already talked about this cost of LCOE of solar cell, and which has been very impressive. So let me not repeat that. But what I like to show you now in next couple of slides is something very interesting. Now, if you look at the total cost of the system at a worldwide level, this analysis done by IRENA, you could see that India though that is not the highest manufacturer. Remember when we talked about the manufacturing in the last lecture, it was China which is primarily the manufacturer of the whole of this solar cell panels specifically. So solar panels are primarily getting manufactured in China, as you would remember, some of you would remember from the previous lecture which we were discussing. While that is a fact, the cost of generation of the electricity in terms of euro per kilowatt peak is cheapest in India. So while solar expansion has drastically reduced the technology cost, fall in solar cost has been quite dramatic, and this is primarily because of the exponential growth of manufacturing in India. India has been still, though it has been out of manufacturing race, but it still has the lowest LCOE, and that is something which is interesting for us to understand. And when we meet in the next class, we will start looking into this aspect before we go further into India's further analysis, that what is happening at a policy level, what is being achieved in India, what is being done in India, and then how we expect this sector to grow in India, and worldwide how do we expect it to grow, what are the challenges around this specific sector, and how does it, while we are talking about this to be kind of our backbone of energy transition, is the journey very smooth, or are there some hiccups that we anticipate on the way? Thank you, and see you in the next class.